Welcome everyone. Today we'll be learning about telecommunications. So let's begin. So what is networking? Let me just tell you about communications and then we can talk about the differences. So communication is when you have a transmitter and then you have a receiver. So there's only one there for communications. You only look at one, how these two are communicating. So you have transmitter and receiver. For networking, it's two or more nodes. So we call these nodes 1 and 2, but for networking we have two or more. So you can have different, and how they communicate, that's the issue. So you have 1, 2, 3, 4, 5. So how they send information to each other, that is what we're going to be looking at. So you have 1 maybe trying to get to 5. So how is it going to do that? What's the routing? Is it going to go 3, 4, then 5? Or is it going to take another route, 1, 2, or 5? So there will be many issues that we're going to look at. So let's begin. So why are we focusing on this? So if we think of the internet, it has a lot of devices, millions of connected devices. So how are they connected? That is important. So you have many devices connected, and not even inside your homes you have many, and maybe you have countries, all of the places inside a country. You have different businesses, you have homes, you have schools. They're all connected to each other, and we're going to be they all require networking. So that's what we're going to be looking at. So we know that devices, they have Wi-Fi. That's how you connect. You need Wi-Fi. Sometimes you need Ethernet. You need satellite, connected to the satellite. So these are things that connect others. And internet, we have packets. They send packets, and that's how devices, they communicate with each other, by sending packets of information. So there are different types of networks. So communication networks. So you have so we have this diagram. So let me just do that quickly. Communication networks. So we have switched networks. And inside those switched networks we have circuit switched. So let's look at circuit switched networks. So circuit switched networks is when you have one end of the device, it's trying to communicate to another end of the device, but how that does it through circuit switch. So there's like a circuit running through. So you have maybe this device and it's connected to a circuit. So this is a circuit from one place to the other. and from another signal from this end of this, you have another, let's just say your friend. Okay, so you have a friend here, you have you're here, and you want to talk to your friend who's on this side. So first you send your signal through this is the router, let's say, and then it'll go to this router, and then it will go to this router. So these routers are connected to each other, and they have like a dedicated resource. So using that dedicated resource, there's like, maybe let's say there's like 3 dedicated resources, and once you want to talk to your friend, you'll need to borrow that dedicated resource. So you'll send it through, and then you'll borrow this line, let's say the top line. Okay, so borrow the top line, and then it'll be using this. So this is, no one can use it. Once you've connected to your friend, no one can use that top or that route that you've used. So it's blocking other networks from using that. But you can, the other one, they can use the bottom one, okay, and to go through the network. But if all of these are full and you're trying to connect to the circuit, then you won't be able to. You'll have to wait. So that is circuit switch networks. And you have another example of switch networks is packet switching. Okay, packet. So this is when you send information and you send it through packets. So your whole information that you are sending, maybe it's an email, that is divided into packets and then is sent through a circuit, through a network. And so if you have 2 people sending these packets, then it doesn't matter. Once you are switched, you are connected to the network, and he's also connected to the network, it doesn't matter. You'll be using the same circuit, and you'll be sending the information at the same time. You don't need to wait for the other person. It's just all of them can be using it at the same time. So packet switching, you have more, it can be divided into more subsections. So you have a datagram, and you also have virtual. Okay, there's a key difference to this. Virtual circuit network. Virtual circuit. So I'm gonna go through quickly because we'll be going through this in more depth later on. So here for datagram, the key difference is that the route that you are sending, it's not fixed. You can change your route. So if you are sending information, then you're not going to use the same route. The route might change depending on the traffic. So that will make, maybe if one route is more there's more congestion in that route, you can change that route. But for virtual circuit, that is not possible. It's already determined that this is the route that the packets are going to take. It's not going to change. So now let's look at delays now. So we have these packets they're going through. There are a lot of delays that they might face. It's not there are downsides of using packets, but mostly packets are used, internet is used, there's packets. We should know what are the advantages, what are the disadvantages. So let me just do a simple diagram to represent how packets are traveling through. So let's say you have computer A and computer B. So computer A, it's sending information, okay, as packets. Okay, so let's just say that the packets for A is colored. Okay, so it's going through this it's traveling this way, and then it's going this way. Okay, and then it's going to travel through that line to maybe a router. Okay, so this packet, they're going to be coming here, and it's also going to come in here, and it's going to join a queue. Okay, it's going to join a queue here, and they're just waiting to get onto this queue, and then they will be going through this line. Okay, so there's a queue here, and the packets, they can come here, they can join this area. Okay, this is free, they can come and join. So there's a queue here, that's one delay, and there's also processing delay. So here it's traveling through this line, so this is called a propagation delay. Propagation delay. This is a queuing delay, and there's a processing delay. So here it'll be processing, and then it'll be here. What's happening is that it's going to transmit onto the line. So that is called a transmission delay. There's some transmission delay. Okay, so these are the delays, and there are formulas that we need to know. For the transmission delay, we know that this is a network medium. Maybe it's like an Ethernet. Okay, this could be an Ethernet, and you need to first put the packets onto the Ethernet, and that will take some transmission delay. So let's call the transmission delay TTR. Okay, so TTR, that has a formula. If you want to work it out, it's the packet length L divided by the bandwidth of the Ethernet. So that's bandwidth, we call that R. Okay, so it's the packet length, so how much is that packet, how many bits is it, divided by the bandwidth. So it's L divided by R. These are important formulas. And then we have the propagation delay. So we have it here. It's traveling through the Ethernet or whatever medium. We have that as, let's call it TPR. Okay, so TPR, that is equal to the distance that is traveling divided by the speed of the bit. So yeah, I think that should be easy to understand. So we have an example for this. I'll just quickly go over it. I'm not gonna write it down. So imagine you have 10 cars. They're all joined together. They're all going at once. So there are 10 cars and they are traveling at 100 kilometers per hour. So 10 cars, they're all traveling at 100 kilometers per hour. So they go through a tool booth, and so what the tool booth does, it services the car and it takes 12 seconds. So there's 10 cars and it needs to service these cars and it takes 12 seconds. So that will take, in total will take 120 seconds. That's 2 minutes. Okay, once it does that, now the cars, they're going to travel 100 kilometers and they're going to arrive at the second tool booth. So what's the total time that it takes to get to the second tool booth? I want you to think about that. So they took 2 minutes on the tool booth for the first tool booth, and then now they're going to travel 100 kilometers per hour. So what's the total time? So you have 2 minutes and then you have 100 kilometers per hour, and they're going at 100 kilometers per hour, and now they're going to travel 100 kilometers per hour. So that's 60 minutes. So 60 minutes plus 2 minutes, that's 62 minutes. That's the total time. So with that example, you can understand that you have the propagation, the packets they're propagating, that's the time, and you also have the processing. So how long does it take to process each packet? So you have L divided by R. So L is like how many there are, and R is like what time does it take. So R is like how quick it does it. Okay, so the internet, it uses these packet switching. You have this happening all the time. And how does it do it? There's like a protocol that it follows, and that's what we're going to be learning about. And that is you have that as the. So we need to make sure that when you're sending packets, they need to follow the same instructions, and you also need to have a protocol in place so that it doesn't it can run smoothly. So let's look into that. So we've talked about the internet. We learned how the internet works. So different networks. We have looked at switch networks, packet networks. Now we're going to look at the protocol. So the protocol that we're going to be looking at is called the TCP/IP reference model. So you have this model, and we're going to be looking at each of the layers. So these are very important layers. You have the application layer, you have the transport, you have the IP layer, you have the network access or network access. Let's just go with that. Network access, and you also have the physical. So we're going to first go through the bottom one, physical, then we'll go to the network access, then we'll go to the IP, transport, then application. So the physical layer, that is the most that's the one we see with our eyes. So you have packets going through, they can go through the transmitter. You have a transmitter, and then you have a receiver. So you have the physical. How are they connected? Are they using a twisted pair, coaxial cable, optical fiber? How are they connected? So you have the transmitter and then you have the receiver. How are they connected? As the physical. Maybe there's no connection. It's Wi-Fi. It's just it's propagating through the air. And so this is like the simplex. One is the transmitter, the other is the receiver. This is the simplex. You have the half duplex, so they're both transmitting, but they do it like at one at a time. So first this transmitter, after it's done the transmission, then this will have the chance to transmit. Or you have another one, that's the full duplex. Both of them can transmit at the same time. They don't need to worry that they need to wait for the others. Okay, so that's simplex. One is transmit receiver, the other one is half duplex. So they have to wait for each other's turn. And then you have the other one. So you have this sending and this sending. It doesn't matter, they can do it simultaneously. So we have keywords. So we're going to be looking at sending digital data, and then we'll be looking at sending digital data, and then that digital data it'll become digital signal. So we're going to be looking at that. So now let's look at the different types of media. So these are the media, okay? These lines are connecting the transmitter and the receiver. They're called media. So we're going to be looking at media. So you have a guided wire. So it's guiding the data, the packets to where it's going, like a tunnel that's guided. You also have wireless. So it's going all direction. Okay, we won't be looking at wireless that much. So for guided, the medium is important. What type is it? Some are better than others. So the way you're designing them is important. So maybe we're going to be looking at that. So your guided media. So guided media, the first one we're going to be looking at is it's the twisted pair. So we're doing the physical right now, okay? So we're twisted pair. The twisted pair, it's the most common medium, and it's used in telephone networks. It's used within buildings. They're using twisted pair to connect, and is used in LANs, so local area networks. So the pros are that it's cheap, it's easy to work with. There's but the downside is low data rate. It has a short range, so trying to send it to like maybe somewhere far away. Your signal might deteriorate before it gets there, and you'll need a lot of amplifiers if it's analog, and to strengthen the data when you're sending it. So there are different types of twisted pair you can look into. You have the unshielded and the shielded twisted pair. So the unshielded is ordinary telephone wire. It's the cheapest, easiest to install. However, it suffers from external EM interference. You have the shielded twisted pair. Is metal braid, and that reduces interference. It's more expensive and it's harder to handle. Okay, so that is all about the twisted pair. And we have the coaxial cable. So that is it's another form of guided media. So people use that, and they use it for different things. You have different needs. You need to think which is your need. Some of them you might use twisted pair, some of them you might use coaxial cable. So let's look at the need. So it's used in television distribution, for long distance telephone transmission, short distance computer systems links, and also it's used for LANs. So the pros are that it's good noise immunity, it's harder to install, however, and repair, and there's a moderate cost. And there's another one, which is the optical fiber. The most people, they say this is the best optical fiber. So it has a greater capacity, a smaller size and weight, lower attenuation, and almost independent of frequency, has a greater repeater spacing. So the applications are long haul trunks, metropolitan trunks, subscriber loops, and LANs. So that's the guided media. Now you can have the unguided. So we all know unguided media. We all use it every day, the Wi-Fi, and you'll have like a transmission and reception. And how are they doing it? They're doing it using antenna. So you have antenna and then another antenna, and that will try to detect the signals that are coming to it. So you have directional, so focused beam onto that, or you have omnidirectional, signal spreads in all direction, and then it can be received by many antenna. So that is the physical. Now let's see how you actually send the signal. How are you sending the signal so that it's being received correctly? So we're going to be looking at digital data. Okay. So we'll keep this. So transmitter and then receiver. How is the data going through? So we're going to be looking at digital data. Okay, what is digital data? So you have ones and zeros. Okay, so this is digital data, and you have a transceiver, and then it's going this way, and then you also have the digital signal. That's how it's being detected. So you send bits, right? 1 2 1 0 1 0 1 1 1 0, right? That, and then that's going through as digital signal. So like that. So how we sending is very important. It's all about synchronization. So the transmitter and the receiver, they need to be in sync. If when the transmitter sends a 1, the receiver needs to pick up that 1. So it needs to sample it. So sometimes it can become out of sync, and that is not what that's very downside. So we need to make sure it's kept in transmission. it's synchronized. When it's transmitting, it's always synchronized. Sometimes the receiver its clock is 1% faster than the transmitter's clock. So maybe if it's because it's 1% faster, after a few times it's sampled, it will be sampling the wrong data. So it might be first it'll sample, the receiver sampling this, right, this data, and then because its clock is 1% faster, after like 50 or more cycles, it will sample the wrong data. It'll and then you will get wrong outputs. So we don't want that. We need to use a technique where when it's sending the information, it can detect like if it's become out of sync. So we have different ways that we can send our information. The first one is the non-return to zero level. It's called not return to zero level. So what is that? So if you're sending, let's say you're sending this data, okay, 0 1 0 0 1. So non return to zero level. What this means is that 0 is high and 1 is low. So if you have this, you're sending 0 1 0 0 1, whatever that is data. 0, we said that is high, 1 is low, 0 is high, and 1 is low. That is the signal that we're transmitting. And we have another one. So that's one way of sending. We have another one which is non-return to zero. Non-return to zero, and it's invert 1. Okay, invert on 1. So let's say you're sending the same one, 0 1 0 0 1. Okay, so what this one is about is that, so you have 0, that means no transmission, and 1 is transition at start of bit. So let me just show you the example. So when it's a 0, it will be no transmission, and when it's 1, it will be high, and when it's 0, that means there's no transmission, so it will just say the same. When it gets to 1, because here it was high and now there's a 1, it'll become low. So why did this go high when it's a 1 and here 1? Because we assume that before it was it did already a -1 before like when it was a 1. Okay, so first was a 0, no transmission, it was already at -1, and then when 1 came, it got high, and then no transmission, and then it changes. So 1, we can say that you do the opposite. So it's transmission at start, at start of bit. So you're doing like a transmission. So first you were sending a 0, there's no transmission. Then when it's a 1, you'll send a 1. Now, because it kept on being 1, you'll know that it's a 0 0. And then now you got a minus. That means you got a 0 here. That means 1 must have come. Now, what's next? It'll depend on the bits. So you see these two, they're different signals. So there are some pros and cons of using this. So it's an efficient use of bandwidth, and it's easy to implement. However, the problem is due to DC component. You see here, it's always the same, so that can be a problem. And here as well there's a continuous. So continuous is not good, because sometimes because it's continuous, there might be noise and it might just go down and then up, and then what can happen is that you don't know. Staying at continuous is hard. So if there's problem with synchronization, it's hard to determine the beginning / end of bits. Also, there can be loss of synchronization. It can become out of sync. So this method of transmitting, they can be out of transmission. So we need to think of other methods that are more efficient than this. So we've done non-return to zero. Now we're going to look at some others. So you have a multi-level binary. So here, before it was 0 and 1, now we're going to add another level. This first one will be bipolar AMI. So what you have is that 0, if you're sending a 0, that's no signal, and 1 is a positive or negative signal, and it must alternate. So what does that mean? I will give you an example and then you'll understand. So let's do it again. We're sending 0, 1, 0, 0, 1. So 0 is no signal. So here, because we're looking at more than 2 levels. So you have the high, you have the 0 level, you also have the negative level. Okay, so there are 3 levels this time. So 0 is the no signal, 1 is the positive or negative. So how do we know if it's positive or negative? Well, before this we assume it was negative. Okay, so because it was negative, it must alternate, so it will be a high, then this is no signal again. Because this was positive, this one will be negative, and then we don't know what's happening next. So that is bipolar AMI. We'll look at the pros and cons, but let's look at another one. It's the pseudo-ternary. Ternary. So here, this time, 1 is no signal, and 0 must be positive or negative, just like the other one. Okay, so basically the opposite. So let's see how that looks like. So again, high, you have 3 levels: high, no, and then you have negative. So we'll assume same assumption, and now it's 0. So it's positive or negative, and then signal, and it must alternate. Okay, so 0, let's just assume that it was negative, then now it's high. 1 is no signal, and now because this was high, because now it's going to alternate, so it's 0 and another 0. So what happens is go back up, and then no signal. So here, this is the path. It's a bit different to that. I wouldn't say it's opposite to that. So what are the positives of this? Well, there's there's not that much DC component. There's no DC component. Here is fine because that's 0, no signal. That doesn't really matter. Here is going up and then down like that, up and then down, up and down like that. There's no DC component. Also, there's good synchronization with long ones or long zeros in the pseudononary. So there's good synchronization. Here is positive. Now you know that because this was positive, this should be negative. And this can be used for error detection. If this was positive and then you have another 0 and then you get another positive, that is not possible. You can say that there's something went wrong. So yeah, it should be a negative. If there's a positive again, you can say that there was an error. But it's not as efficient as the other one that we looked at before, because here there are 3 levels, and that requires more data. Okay, let's look at another one. So this is how we're sending information. We're sending bits, and the way we send it, it's through signals, right? And you can send it as one high or low, or you can only send it as maybe just highs. So now let's look at another one. This is called, this is self-clocking codes. So you have Manchester. So this is, let me just write self-clocking. That's important when we're looking at these self-clocking. Sub-byte. So first you have Manchester. This is a very easy one. Manchester. So what this one is, when you're sending a 0, what happens is that you're going to go down, and it's going to go through the middle, okay? So you're sending that 0, it's going to go through the middle, so it's going to go down, okay? So you're sending 0, what happens is it's going to go down. And 1, what's going to happen is it's going to go up in the middle. You do it from the middle. So 0, it goes from a high to a low in the middle of interval. And for 1, it goes from a low to a high in the middle of interval. So it's used in many LANs. So let's see if we're sending this data 0, 1, 0, 0 and 1. So we know that when you're sending a 0, what's going to happen is going to go from high to a low, and for a 1, it's going to go from low to a high. Okay, so you see what happened is going through the middle. It's changing in the middle. And 0, what's going to happen is it's going to go from a high to a low. And here again, how is that what's going to happen? Well, this is going to go up again, and then it's going to carry on, and then it's going to go down. So it becomes a high again because you're sending a 0. And here you're sending a 1. It goes from a low to a high, so it can just carry on. So that is when you're sending a 010 through at Manchester. So you have another one, differential Manchester. So there's it's a bit different. So you're sending you might be sending a 0. How that works is the transmission at beginning of interval, and 1 is absence of transmission at the beginning of interval. And that is used in LANs as well for like token ring. So let me just show you an example how this works, and then I can explain it. So you're sending again 0, 1, 0, 0, 1. Okay. So if you're sending a 0, what's gonna happen is it's gonna go down in the middle. It's gonna go up, and for a 1 it's going to continue. It's going to continue and then it's going to go down. For 0 it always goes up and then down and then again up and then down. But for a 1, what happens is, because it's first low, it's going to carry on being a low, and then it'll swap. Okay? For a 0 it always goes it goes from high, it always goes a high. So here, because it was it started here, from 0 it'll go, because it'll go up and then down, and here because it was 1, it was going down and then it'll go up, carry on, and then like that. Yeah. For a 1 it carries on wherever it was at before. First it was high. For 1 it'll carry on here as well, because it was at 0 it'll carry on, and then because it was low, it was at the bottom, it'll go up. But for a 0 it's a bit different. A 0 it always goes up, down. It'll go up and then it'll go down. At the start it'll go down and then up. Okay, so there's disadvantages to this. The first one is that you see how it's keep on swapping each in the middle, and even at the half interval is swapping. So that is, you'll need a double bandwidth for that, because it's changing very quickly. It's not changing like for the other one, it was like all of 1 down is bigger, right? For the other ones it was bigger. Here it's very tiny, so you'll need double the bandwidth. There can be error detection for this, so it's useful, but it requires more bandwidth. So that is like the physical protocol. You have all of these things that you can use. So depending on which one you use, you'll need to work them out. So time, you alright?
10:32.
Okay, so the next one we're going to be looking at is network access. It's also called data link layer. Okay, so we're going to be looking at the data link layer. So the job of this data link layer is so 2 points, 2 devices, okay, how are they communicating? So there's a direct link. We want this direct link. If you have this direct link, how are they going to be communicating